Okay. So we're still in the 3.8. We'll finish that today. We'll hopefully start and finish 3.9, but I don't know. Finish 3.8, 3.9 maybe. We still got to cover that, and 3.10, 3.6, 3.11. So we have quite a bit of ground to cover in the next few days. Does anyone have any homework questions? Yeah.
Number 19 on 3.7.
Okay, so calculate the derivative of the following function. We're taking the derivative of y with respect to the variable p, or we can write that as the derivative with respect to p. Okay, so y prime is, what rule are we going to use here to take that derivative? Yeah, we've got a product rule. Initially, because we've got the product of two functions, the p plus pi to the fifth and the sine of p to the fourth. So take note of the different notations here. Like if they write sine of p to the fourth, what they mean is sine of the quantity p to the fourth. Whereas if the power is attached to sine, so if it's like sine to the fourth p, what that means is sine of p, and then that whole quantity raised to the fourth. So no, the notation's kind of weird how they decided to put the power next to the function, but that's what it means. So this is sine of p to the fourth. So we've got our first times the derivative of the second plus the second times the derivative of the first. Okay, so that's what the product rule tells us, to take the derivative that way. And then once you find these other derivatives that are showing up from the formula, you're done with taking your derivatives. So separately, off to the side, whatever, we've got to compute the derivative of sine p to the fourth and p plus pi to the fifth. So the derivative of sine of p to the fourth. What would that derivative be? How do we take the derivative? What rule is involved?
Cosine 4p to the third. Can you do the chain rule?
The chain rule, right? Because
are
it's
those two separate. Are they
yeah.
Two, so it would be like a chain rule at the bottom.
Right. This is like the sine of u, where u is equal to p to the fourth. So that's the composition. Sine is the outer, p to the fourth is the inner. So we take the derivative of the outer, derivative of sine is cosine, and we leave the inside alone. And then we multiply by the derivative of the inside function, derivative of p to the fourth. Is everybody all right with that? Okay, derivative of p to the fourth now, that's just our power rule. We've got 4p cubed times cosine p to the fourth. Okay, so that's one of the derivatives we're going to put in from our product rule. Any questions on that? And then the other derivative that showed up from our product rule was, what was it? P plus pi to the fifth. What rule is involved here? Another chain rule. We have the derivative of the outside, leaving the inside alone, times the derivative of the inside. With respect to p, what's the derivative of p plus pi?
1.
Just 1, right? Derivative of p is 1. The derivative of pi, it's a constant, is 0. I'll just put this here. Do you have a question, Jim?
No, you kind of answered it.
Okay.
So maybe just,
So this thing right here is the derivative, we'll just write it out, derivative of p plus the derivative of pi. And that's 1 plus 0. So that derivative goes in for our product rule as well. Any questions on that? So our derivative we're looking for is p plus pi to the fifth times 4p cubed cosine of p to the fourth plus our sine p to the fourth times our 5p plus pi to the fourth. They should accept, my math lab should accept that as the answer. I did some sporadic problems just entering various forms of these, and I never had an issue with it just wanting me to simplify or factor out anything, so that should be good enough.
would you accept that on the test, or would it?
Yeah, I would prefer something like that on the test, because when you start simplifying it, you know, there's going to be so many varying answers. Plus, the further you go with these things, you know, just there's the likelihood that you're going to make a mistake somewhere. So, if the instructions say to find the derivative, just find the derivative. I'll say do not simplify, or I'll say find the derivative simplified. So it'll be clear as to when find this derivative, don't simplify. This is where you would stop. Okay. Any other questions on that problem? Other homework questions? Yeah.
Number 5 on 3.8.
3.8, number 5. Okay. Are there any more homework questions from 3.7? Number 5. So use implicit differentiation to find the derivative. Means here I know it's in two parts, but this first part entails that we solve for y prime. And then find the slope of the curve at the given point, 1 pi. So we're going to take the derivative with respect to x, both sides of our equation. But hopefully the right side's straightforward. We've got 16x cubed. What's the derivative of sine y? Not quite. Remember, this is the derivative. Yeah, you have to use the chain rule. This is the derivative of the sine of y, and y is some unknown function of x. So how will we take the derivative of the sine of f of x? What would the derivative of sine of f of x be?
Like cosine f of x, right?
Partially, right?
Times f prime of x.
Yeah, so we have cosine of f of x. There's that's the previous problem. There's the cosine of p to the fourth, and then we had to multiply it by the derivative of p to the fourth, right? So we have to multiply this by the derivative of the function. The chain rule is in every derivative we've ever done up to this point. Even before the chain rule, you were doing the chain rule without knowing you were doing the chain rule. Right? So it might be worth mentioning, just as a side note, when you take the derivative of I don't know, x cubed, let's say. The derivative of x cubed, we said by the power rule 3x squared. Right, but what we're really not seeing there is we're multiplying by the derivative of the inner function here, which is just x. And the derivative of x with respect to x is 1, which is why we don't see that. But we have been doing the chain rule. Every derivative involves a chain rule, if you think about it. Does that make sense? I think if you can think of like derivative of x cubed as a chain rule, it's redundant and not necessary, but it can help you understand that whatever your argument is, you've always got to take the derivative. When you take the derivative of something, you always got to multiply by the derivative of your argument. So it's the derivative of this sine f of x, we take cosine f of x, but we have to multiply it by the derivative of the argument, which is f prime. So the derivative of sine y is sine y times y prime. The derivative of x cubed is 3x squared times x prime.
Did you mean cosine y? Or?
Yeah, cosine. Sorry. Yeah, so we take the derivative of the outside. So, questions on that? Okay. Then we solve for y prime. The y prime is 16x cubed over cosine y. And then part B says to find, find the slope of the curve at the point 1 pi. So evaluate y prime for x equals to 1, y equals to pi. 16 times 1 cubed over cosine of pi. Gives us what? 16? What's cosine of pi?
Negative 1.
-1. Yeah, so negative 16. So, the notation, you might see a bar here with the point here, just so we're clear that we're evaluating y prime at 1 pi, 1 comma pi, and it's not just y prime. So this notation is use y prime evaluated xy. So that's the slope of that curve sine y, etc., at that particular point. So let's look at that curve. Not terribly crazy. And our point was 1 pi. So we have the tangent line coming through here like this. It's negative. Any questions on that? Any other questions from 3.8? Any other homework questions? So we were looking at implicit differentiation, and the problem was to find the second derivative of the equation for our unit circle. So what these boil down to is expressing higher order derivatives as a function of x and y as well. But don't express the higher order derivatives with derivatives still in there. It's kind of akin to solving for y, but you still have y's on the other side too. So we found the second derivative of negative xy using the product rule. Sorry, we actually used the quotient rule. Here we could use a product and a chain rule for the negative xy to the negative 1. But we used the quotient rule, and when we used the quotient rule, we came up with the y prime. And we were working on getting rid of the y prime to express y double prime as a combination of x and y. So we went back up to our previous derivative here and said, well, let's change y prime into negative xy. And now we've got complex fractions. So let's multiply through by y over y so we can clear that negative x over y in the numerator. So we have, well, let's write this out now. So we're going to distribute that up top. Y times negative y is negative y squared. That y times x, negative x over y, is negative x squared, because the y's cancel out. And then we've got y cubed on the bottom. Okay, so that's our second derivative. Technically that's our second derivative. We could simplify it so that it is simpler than how we have it by going up to the original function. And if you remember, the original function was, or the original expression was, equation rather, x squared plus y squared equals to 1. So what would negative x squared minus y squared be? So let's just factor out a negative from both of those. And we have y squared plus x squared times negative 1. What's y squared plus x squared? Yeah, we're given what y squared plus x squared is. That's the original relation. Y squared plus x squared is equal to 1. So we're given this. So really, y double prime is negative 1 over y cubed. Which is much simpler than anything we got as a representation for the second derivative. So it really depends on the function. Sometimes the derivatives depend on both x and y. Sometimes the derivatives just depend on x or y. Problems like this where you do have to find the second derivative, you want to make sure that you're also looking at what the first derivative is and plugging that in to simplify. And after you've gotten rid of the first derivative, oftentimes you can go back to the original relationship and use that to simplify even further. So are there any questions on this example? We'll look at one more, close out 3.8. So we want to find the derivative. We're going to take the derivative of the equation derivative of negative 8x is negative 8. Maybe we need to think about the derivative of sine of 2y squared and the sine of 5e to the y. So let's compute the derivative of the sine 2y squared. So what would the derivative of the sine of 2y squared be?
Cosine of
Y squared plus y prime times y prime.
Cosine of 2y squared
Plus times y prime.
times,
Y prime.
well, it's not just y prime. What does the chain rule say we have to multiply this by?
The derivative of the inner.
Times the derivative of the inner. So what is the derivative of the inner?
4y.
times y prime. So there's the derivative of the outside, leaving the inside alone. So it's y to the second power, left that alone, times the derivative of the inside.
So the derivative of the inner always counts with the y prime.
Mm-hmm. Right. Yep. I mean, if it's something like 2y squared, yeah.
In what case would it not be? I mean,
Well, at some point it will be, but that's when you're taking the derivative of something that involves y. Like if it involves 2y squared, or if it involves x times y, you know, those things are, yeah. But anytime we take the derivative of something involving y, we take the derivative normally and then just multiply it by y prime. Okay. It's the same idea. If we take the derivative of 2x squared, it's 4x. Normally we would say it's 4x, but we're also multiplying it by the derivative of x, which is 1. So it's 4x times 1, and we just say that's 4x. Okay, so the derivative of sine of 2y squared is cosine of 2y squared times 4 times y prime. Any questions on that? Yeah. 5e to the y. Remember, we can write that since the 5 is a constant, we can take that 5 out. 5 times the derivative of e to the y. So what is the derivative of e to the y?
E to the y.
What's a large y prime?
E to the y times y prime. Take the derivative normally, multiply by y prime. Same thing's true. If I take the derivative with respect to x of e to the x, we know it's e to the x. But what we're not seeing is it's e to the x times the derivative of x, which is 1. So that's, those two derivatives need to go in place up here now. So that's cosine 2y squared times 4y prime equals to 5 e to the y times y prime. More space. Do y'all have any questions on that? So you really have been doing the chain rule the whole time. It's just your x prime, as in place of the y prime, has always been 1. That's why we've never seen it. Okay. Now we have to solve for y prime. Just means the terms that involve y prime, we need them together on one side, and the terms that don't need to be on the other side. So it doesn't matter what side they're on. Let's just say it's cosine 2y squared times 4y prime minus 5e to the y prime equals to 8. So the terms that have the y prime on one side allows us to factor out y prime. So we're factoring y prime out of those two terms, and then we're going to divide by what's left over. So cosine 2y squared times 4y minus 5e to the y. All that times y prime equals 8. The idea of implicit differentiation, the practical uses of that is when we look at related rates. So when we're trying to relate two rates of change to one another and solve like a physical application, implicit differentiation is used in those settings where your variable is t. So we take the derivative with respect to t, and we might have x, y, and z in an equation, but they're all implicitly differentiated with respect to t. So if we do have time to cover 311, we'll definitely see this again. Granted, the functions aren't as complex, but just divide by that quantity. So the derivative is 8 over cosine of 2y squared times 4y minus 5e to the y. I kind of hope the solving for the y prime is sort of secondary. I really just want to make sure that everyone's okay with the process of taking the derivative implicitly. Are there any questions on it? Well, then we'll end 3.8 and start 3.9. In 3.9, we're looking at the derivatives of logarithms and exponentials. We've seen thus far the derivative of one particular exponential. So here we'll look at the derivative of all of the other exponentials, like what's the derivative of 2 to the x power? So some properties of the exponential base e and its inverse natural log is given there. We do end up utilizing these properties to sort of justify our derivatives. So instead of looking at the definition of the derivative, the limit as h goes to 0 on the difference quotient, we're going to justify the derivatives in this section by other techniques that we've learned up to this point instead of using the definition. So the first function we're going to look at is the natural log. I'm going to find the derivative of y equals to the natural log of x. Now again, just so we're clear, the derivative is defined as the limit as h approaches 0 on the ln of x plus h minus the ln of x all over h. And that's a very difficult thing to do. So instead, what we'll use is the fact that if the y is equal to the natural log of x, what's an equivalent way to write that equation? Just from an algebraic standpoint, if y is the natural log of x. The equivalent way to state that, or the y is the natural log of x if and only if what's true?
X is greater than 0.
That's the domain of the natural log, x has to be greater than 0, right? I'm looking for the equivalent way to write
X equals e to the x.
x equals to,
E to the x.
close. It's right here in number 2. If y is equal to the natural log of x, if and only if x is e to the y. So do you remember, I don't know, the mnemonic sometimes is rolling the logarithm. Do y'all remember that? To convert a logarithmic equation. So if I have, this is really the log base e of x equals to y. In order to convert a logarithmic into an exponential, we take e to the power of y and set it equal to x. Right, so we roll the log. What if y were the log base 5 of x? What is that equivalent to?
5 to the power of y equals x.
Yeah, 5 to the power of y equals to x. Okay, so we don't know the derivative for the y equals natural log of x, but we can equivalently express that as e to the y equals to x. Can we find the derivative of e to the y equals x?
The chain rule.
Yeah, chain rule is used here, particularly the process of taking the derivative of e to the y equals x. What are we using? Give you a hint, we just did it. Yeah, implicit differentiation. So implicit differentiation on e to the y equals x, you just take the derivative of both sides with respect to x. Derivative of the right is equal to 1. What's the derivative of e to the y?
E to the y times y prime.
Yeah, we just did that one too. E to the y times y prime. Then we've got to solve for the derivative, right? We solve for y prime. So y prime is equal to 1 divided by e to the y. But we don't want to say that that's our derivative, right? We don't want to say y prime in terms of y. What's y prime in terms of x? What's y prime with just x's involved? Yeah, it's 1 over x. How do you know?
Because x is equal to e to.
Right, because x is e to the y. So we've got 1 over e to the y. So it's y prime is 1 over x. So if y equals the ln of x, y prime is 1 over x. Now pay attention here, because what you're really doing is this is the derivative of the log part. The chain rule is still in effect here. Derivative of the natural log of x is 1 over x. What we're not seeing in this formula is we still need to multiply this by the derivative of x. It doesn't make a lot of sense to think about it here. Let me restate that. It doesn't make a lot of sense to write that here, But it makes perfect sense to think about that process being involved here. Okay. So I'm just going to go ahead and erase this, because that's 1. But keep in mind that's what we're doing. Now, of course, we're not going to see functions just as simple as ln of x, right? We're not just going to be taking the derivative of the natural log of x over and over and over again. We're going to think about x in terms of the chain rule, where that's actually a function of x. So the more general derivative that applies to us is, so let's say in general, if y equals to the natural log of any function of x, whether that's x, whether it's x squared, whether it's whatever, then y prime is 1 over the argument, right? Just like ln of x derivative is 1 over the argument, and then what else do we need here?
The derivative of the argument?
Yeah, the derivative of the function, derivative of the argument. Or often it's just expressed as the derivative of the function over the function is how we take the derivative of the natural log of something. So this is what we want to think about the derivative of the natural log is. Or if you think about it in words, the derivative of the natural log of whatever this argument is, it's just 1 over the argument multiplied by the derivative of the argument. You don't necessarily need to remember this process. You need to remember the formula we just wrote down. The derivative of the natural log of a function is the derivative of the function over the function. But with other techniques that we've learned, we can justify derivatives outside of just using the definition of the derivative. Do y'all have any questions at this point?
Is this only for the natural log?
Yeah, only for the natural log. When we look at general logarithms, like the log base 2 or the log base 7, then they're a little bit different. No, they're not much different, they're just a little different. So some examples. We'll find the derivative of, let's start off with the function y equals to the natural log of x squared. So the derivative for the natural log of any function, as we just wrote down, is 1 over the argument of the logarithm times the derivative of the argument. So just be careful here. I see a lot of people take derivatives of logarithms or natural logs like this and still have a natural log in it. The derivative of the natural log doesn't involve a logarithm. It's just 1 over the function's argument times the derivative of the argument. So we have 1 over x squared times 2x. And then we can simplify it because we've got 2x over x squared. So we've got 2 over x.
That's it?
That's it.
That's very nice.
Would you take it as 2x over x squared if we forgot to simplify?
No, it's stuff like that, with simplifying stuff like that, you should do that. That's pretty basic. It's like saying 10, this is like leaving an answer like 10 over 5. You should say that's 2, right? When I mean simplify, I mean simplifying something like, e to the x sine x ln x minus cosine squared e to the x to the second power ln of x to the fifth power, stuff like that. Like obvious, trivial things, you should simplify.
Just get dumb on tests and make stupid mistakes.
Also, if y equals to the ln of x squared, do you all remember properties of logarithms? Somewhat? You should be familiar with them. If not, they're used heavily in this section. If I take the log of anything to a power, what can I do to the power?
You can move it in front.
Move it out front. So by properties of logarithms, y equals ln of x squared is the same thing as 2 times the ln of x. So another way to look at this is to say, well, instead of taking the derivative of ln of x squared, let me first simplify the function with properties of logarithms and call it 2 ln x, and then take the derivative of that instead. So y prime is 2 times the derivative of just the ln of x, right? What's the derivative of ln of x? 1 over x. So this is 2 times 1 over x, or 2 over x. So really, those properties of logarithms are utilized in this section. There's technique of differentiation called logarithmic differentiation, which solely, or not solely, but heavily relies on properties of logarithms to simplify first before you take a derivative. But either way you look at it, you still get the derivative as 2 over x. How about y equals to the natural log of sine x? What would the derivative be?
Cosine over sine?
Yeah, good. Derivative of the natural log, 1 over the argument, times the derivative of the argument. Oops, getting ahead. So 1 over sine, derivative of sine. So that gives us cosine over sine. Remember the formula we wrote down for the derivative of the log, natural log, was f prime over f. So here's f prime, because f is the inner function. So derivative of the inner function over the inner function.
So could that also be cotangent?
Yeah, you can write that as cotangent. Probably how you would see it, honestly, but is anyone in here going on to Calc 2? A lot of y'all, okay. So the idea of the derivative of the log of some function is pretty useful in Calc 2 as well, especially when we start talking about the reverse process of taking the derivative, which we will look at in Chapter 5. So so it's not until a ways away. But pretty much, at least half of Calc 2 deals with where Chapter 5 leaves off in this class. And so the idea of taking a function like cotangent and saying, okay, well, what function did I use, or what function did I take the derivative of to get cotangent is a lot of what Calc 2 is about. It's a lot of what Chapter 5 is about too. So that's like the other pillar of calculus. We had the derivatives and we had the integrals. So if we can think of the process of taking the derivative and reversing the derivative to get ln of sine, then we're well on our way to understanding and working well with antiderivatives or integrals. Any questions on these two examples? So how about y equals to the natural log of e to the 2x? What's y prime?
2.
Yeah, it's 2. What's the natural log of e to the 2x?
2e to the 2x?
Dope.
2x.
Just 2x. They're inverses. Natural log of e to any power is just a power. That's like saying the square root of something squared. So before we even take the antiderivative, or sorry, the derivative, we should just note that this function ln of e to the 2x is just 2 to the x, or 2x rather. So what's the derivative of 2x? It's 2. But let's say you fail to remember that. It's the natural log of a function. The derivative of the natural log of a function is 1 over the function times the derivative of the function. What's the derivative of, Nick, what's the derivative of e to the 2x?
So then it would just be 2e to the 2x?
Right, yeah. So this is 1 over e to the 2x times 2 e to the 2x. And what happens here? The e to the 2x divided by e to the 2x is canceled and we just have 2. You still get there. Just put or. So hold on, there's 2 other derivative rules in this section. There's another derivative technique in this section, and in 310 you get 6 more derivative rules. So it's a lot.
Since there's so many rules, would you let us come in like before the
Oh.
test and write a sheet? Like
Oh.
right before put everything away, just like write everything that we know before you hand out the test? Just because there's so much.
No, you really have to know it all. I mean, you can write it out on the exam once I pass the exam out if you want. But that's why I suggested earlier to start making note cards. So I mean, really, you should right before you go to bed, you should be looking at all this stuff again, because it's a lot, and we're not allowed to let y'all use note cards or formula sheets.
Oh no, not like you come in with it, but you write it out right before the test. Like it's a blank sheet, but you just come in early to write it out.
You're welcome to do that once I pass the exam out.
Okay.
Yeah. Yeah, before the exam, if you already have stuff written out, like you wouldn't be able to use that. I'm sorry, I know it's a lot, nothing I can do. Okay, example 4. Y equals to the natural log of the natural log of x. We can't simplify that first, so let's just start off by saying the derivative is 1 over the argument. Here's the argument. So it's 1 over the natural log of x times the derivative of the natural log of x. Is everybody all right with that? And then take the derivative here. Derivative of now the natural log of x is 1 over x. So I have 1 over ln x times 1 over x, which is typically written as 1 over x times the natural log of x. And then, of course, these things could show up in products, they could show up in quotients. So really it's not like you just have like a bunch of different derivative rules to remember, and it's putting them all together, even at the same time in a lot of cases. Okay.
Natural log
Hmm?
x is 1 over.
Yeah, the derivative of this one here. This one here is the 1 over x. That's where we get that from. But the 1 over the natural log came from here because this was the natural log of the natural log, so we took 1 over the argument here.
So like if you did dx, or d over dx of ln of x over ln of x, then you would have gotten 1 over x over ln of x.
Wait, say that again. The derivative of
ln of x over ln of x.
yeah. Before we did anything with that, I would just say that's 1, right?
No. No. Put the d of the d. Okay, never mind. I don't want to play this game.
Derivative. Yeah, I don't understand. Derivative of ln of x over ln of x.
So, yeah, put the derivative inside was what I was saying. I'll just talk to you later.
Okay.
This is where I'm at.
But you're talking about this, right? Or no?
No.
Okay. Okay. Other questions on this? Okay. Second one we're looking at is the derivative of the function b to the x.
Is this 3.9 or 3.8?
2.9.
Okay.
So I see there's a tendency to get these kinds of functions b to the x confused with our power functions. So, you know, if you have to write them out, power functions are x variable to a fixed power, like x cubed, x to the 1/2. Those are all power functions when the power comes down and we subtract 1 from it. Quite different than exponential functions where the variable is now the exponent. So don't get those two mixed up. They have two completely different rules. And what I see is people want to take the derivative of 3 to the x by saying it's x times 3 to the x minus 1. That will never work. So you've got to compartmentalize power and exponentials because they are different. So let's maybe think about this and then we'll take a break. Our function is y equals to b to the x power. Again, our options are to apply the limit as h goes to 0 on the difference quotient and try to simplify all that, or to look at this in a different way so that we can use other derivative rules on this. Okay. So if y equals b to the x, we got to go back to the inverse properties number 3, which says that if I'm looking at b to the x, I can write that as e to the ln of bx, b to the x. So by inverse properties of the natural log and exponential e to the x, if I take e to the ln of anything, well, not anything, but specific things, they're inverses, and I get what's in parentheses, because the e to the ln is canceling out, basically, right? So I can say b to the x is actually e to the ln of b to the x power. Do you all agree with that, or does that look weird?
Where are you getting e from b?
So this is like, we could also, like, let's say we said, well, this is b to the x. Couldn't I write b to the x as the square root of b to the x squared? Couldn't I write it like that?
Yeah.
Yeah, because the square root of that quantity, it's positive, squared, is just a quantity, right? Yeah? So the inverse relationship between the square root and the square are used to rewrite b to the x in a different form. But it's here, the inverse properties of e and ln are utilized to write b to the x in a different form. So it's just a matter of how those functions look. And so then why is it beneficial to write it like this? We've got to also remember properties of logarithms. So if I'm looking at that exponent, the ln of b to the x power, the log of anything raised to a power, what happens to that power? Up here.
Comes out.
Yeah, the power on b, which is x, comes out front. So why would we write it like that?
I would be right.
That's a good question.
Because we have rules for like e to the something, and then we have rules for the natural log.
Yeah, because we have a derivative rule that allows us to take the derivative of e to any power. We don't know quite yet what 2 to the x derivative is, or 1/2 to the x. We don't know what that derivative is, but we can rewrite it in a form that we're already familiar with. It's e to a power. I know how to take the derivative of e to the power, right? The derivative of e to any power, a function of x power, is e to that very same power. What else?
Multiplied by the power.
Multiplied by the... Close. Think about the chain rule. The what?
The derivative of the power.
Yes, the derivative of the power. What kind of thing is b?
Constant.
It's a constant. So what's the derivative of x times a constant? What's the derivative of 37.2 times x?
1.
0.
32.
Yeah.
Oh,
What's the derivative of 2x? 2. What's the derivative of 12x? 12. What's the derivative of this constant times x?
X. One.
Constant.
The constant. So this turns into e to the x ln b times that constant ln of b.
Oh, because it's like L and B times, I see. what
Yeah,
you're
yeah.
saying. Yes, I see it.
That's like x times 2.
Yes.
Yeah. So there's y prime. It's kind of funky in how it's written. What is e to the x ln of b equivalent to?
P to the X.
What?
B to the X.
b to the x, right. E to the x ln b is this, which is this, which is this. But really, that's not the one we want to think about, because that's missing the chain rule. We want to think about the one that does involve the chain rule. And the only addition here, if I know the derivative of the outer function, when my outer function is an exponential, like 3 to the x, 1/2 to the x, etc., then the only other thing I need to do here with the chain rule is to do what? Multiply it by what would the inner function be on something like 3 to the x? What do you do first? If I say x is 2, you got to plug 2 up here, right? You say, well, that's 2, then I raise 3 to the second power. So really what we're not seeing here with the chain rule is what? The derivative of which part?
X.
X. We're really not seeing this part, but it's there. So we're going to remember this one. If y is equal to some number larger than 0, real number, to the f of x power, then y prime is b to the f of x times the ln of b times f prime of x. So really that's the one we want to remember, because it's more specific. Or sorry, more generic. Does that formula work for e to the x? If y is equal to e to the x, that formula says now this b right here is just e. So how do I take the derivative of b to the x? It says it's b to the x times the natural log of its base times the derivative of the power, which is x. So is that the derivative of e to the x?
Yes.
Yeah, because ln of e is 1, derivative of x, 1. So b to the x, or b to the f, times ln b times f prime. Any questions on that? Again, you don't have to remember the derivation. These properties that we're using to derive these things, you should know. We utilize them quite often, to be honest. But the takeaway here is what we have in red, the derivative of that function. Any questions before we take a break? Okay, let's take a break.
I do my homework and then I go work out. Because I know if I go work out and I still do my homework, I'm not doing it.
I wish I could do that. Particularly my schedule would work that way. I wish it did. Okay.
So then, if we've got b to the x, and remember b is just going to be some real number that's larger than 0. That derivative is the exponential here times ln b times the derivative of the function that's in the exponent. So we find y prime for the function y equals to 4 to the negative x. So we have our formula that says the derivative is the exponential as it is times the natural log of the base, which is 4, times the derivative of the exponent. Okay, derivative of negative x is negative 1. So our derivative is negative 4 to the negative x times the ln of 4.
Would you want us to calculate out what natural log of 4 is, or leave it like that?
No, just leave the natural log in, usually, just so it's exact and not some weird decimal there. And also just be careful that this negative 4 to the negative x is negative 1 times the exponential 4 to the negative x power. And don't get that confused with being part of the exponent. If it's negative 4 to the negative x, then you've got both of those, the negative 1 and the negative 4 to the negative x.
So ln of b was a constant, which is y equals 1. But ln of 4 equals ln of 4. Ln of anything that isn't b will equal that.
Right.
So ln of 5 is ln of 5.
Yeah. ln, well, ln 10 is ln 10. ln of anything but e and its powers is, you'll just leave it as that ln of that number.
So, no, I'm not going there.
Okay. Yeah, how about, well, yeah, let's do y equals to 250 times 1.045 to the x. So what rule do we need here?
Is it a product with a
No.
two rule inside?
Because it doesn't have a constant on the outside, so you can take that out.
Yeah, so it looks like a product, but remember when we say product rule, explicitly applied to two functions of x. The product of a function of x times another function of x. 250 is not a function of x. It's just a constant.
So it would have been a product rule if it was 250x.
250x times the exponential would have been a product rule, yeah. So this is y prime is, let's write it this way, 250 times the derivative of the exponential 1.045 to the x. So So what's the derivative of 1.045 to the x?
1.045x times natural log of 1.045 times 1 times 250.
Okay, 1.045 to the x power times the number ln of 1.045. What do y'all think? And really what we're not seeing is also times the derivative of x, but that's just 1, so there's your derivative.
So if the x were to be like a number, like 2x squared or something,
Mhm.
then we would take the derivative of that, that's
Right.
when we would see it.
Yeah, if it's anything but x, even if it's like we saw in that last example, if it's negative x, which is negative 1x, then you've got to take the derivative of it. Okay, any questions about that? You know, they all have a slightly different flavor because there's so many ways to represent various kinds of functions. What about the y equals to the natural log of 10 to the x? So what rule is involved here? What is what is the function?
Is it ln over 10x?
Yeah, well, close.
Or 1 over 10x?
Yeah, exactly. The structure of this function is just the ln of some other function of x. So we're taking the derivative of the natural log of that function, so it's 1 over the argument times the derivative of the argument. Okay. What's the derivative of 10 to the x?
Maybe 10 to the x times ln 10 times
Right. Derivative here is just 10 to the x times the natural log of 10. To the 10 to the x divide away, and we just end up with the ln of 10.
What rule are you using to create an ln there?
Here, that's the
Yeah.
derivative of b to the x. Oops. So the derivative of b to the x involves the ln of the base. Here.
And b is just a number?
Yeah, right.
Okay.
So the ln part in our derivative didn't come from the ln that was already there, right? The ln part in our derivative came from the derivative of the exponential part. We can also, again, look at ln of 10 to the x. Right, that's the log of something to a power. The power can come out front to multiply the logarithm. So by properties of logarithms, y equals to the natural log of 10 to the x power is the same thing as x times the natural log of 10. So taking the derivative of this is equivalent to taking the derivative of that. And that's just taking the derivative of x times a constant. The derivative of x times 2 is 2. The derivative of x times negative 12 is negative 12. So the derivative of x times natural log of 10 is natural log of 10. So that I think that's why it's important to recognize the structure of the function that you're dealing with, because some functions, especially with like logs and exponents, can be simplified before you take the derivative. And honestly, if you can simplify the function before you take the derivative, it's always going to be an easier derivative to take because you've made it simpler before taking the derivative. Okay. Are there any questions? Let's find the derivative of the function 6 to the negative x sine x. So what rule is involved here?
I'm gonna say power.
Power, remember, power is like x to a number.
Oh yeah, that's right, exponent. I take it back.
Exponent for the 6 to the negative x, but what else?
Product.
Yeah, the overall structure of this function is a product of two functions, so this is a product. So we have the first times the derivative of the second plus the second times the derivative of the first. So when you see a complex function, don't look at all of the little parts that make the function up. Just look at the function as a whole and apply that derivative rule. And whatever other derivatives come up, it's almost like a separate problem. So that's how we know when to stop taking derivatives. Find the derivative of sine x. The derivative of sine is cosine. The derivative of 6 to the negative x is what?
Negative 6 to the negative x ln x.
Yes. So we have the exponential part as it is, times the natural log of the base, times the derivative of the exponent. I'm just going to write the rule for that. What we're looking at there. Well, maybe that's confusing. So let me write, just to tie it back into our formula. Say that's 6 to the negative x cosine x minus 6 to the negative x ln 6 times sine x. That's our derivative. Any questions at this point? could imagine this derivative, for instance, where is that function 6 to the negative x sine x? Where does that function have a horizontal tangent line? Then you have to solve where this function y prime is equal to 0. So that's in chapter 4 where we start looking at explicitly wanting to simplify the derivative, not because we just want to simplify something, but because we have to figure out where the derivative is 0. All right, the final derivative rule is for the generic logarithm, so the log base b of x. And again, we don't know the derivative of that, so a property that we know is if y is the log base b of x, what does that mean? What's the conversion, or what's the equivalent way to write that equation?
by x equals b to the y.
Right. B to the y equals to x. And then we can take the derivative of b to the y equals x implicitly, because we know the derivative of b to the y. What's the derivative of b to the y?
B to the y times ln of y, or ln of b times derivative of y.
Right. Derivative of b to the y implicitly is b to the y times the ln of b times y prime. Derivative of x is 1. So then we can solve for y prime. Y prime is 1 over b to the y ln b. But what's b to the y? X. B to the y equals x. So the derivative of our logarithm base b is 1 over the argument times the ln of the base. 1 over x ln b. Again, what we're not seeing there in that formula we just wrote, 1 over x ln b, is we're not seeing the derivative of the argument of that logarithm, because it's just the derivative of x, which is 1. So if y is the log base b of any function of x, the derivative is 1 over the argument times the natural log of the base. And then we have all of that multiplied by, 1 over f of x ln of base times the derivative of f of x. So that's, again, in accordance of to the chain rule. So it's very, very similar to the natural log. It's very similar to the natural log derivative. So let's write it like this. This is f prime. So we can say it's 1 over f of x ln b times f prime of x. And we could also write that as f prime over f of x times the natural log of b. So notice that the f prime over f was the derivative when we took, when we had a natural logarithm and we took its derivative, was just the f prime over x, right? The only difference with the generic logarithm base b is that we have the ln of b here on the denominator. So this formula said that the derivative of this was f prime of x over f of x, 1 over the argument times the derivative of the argument. So really the only difference is for any other logarithm, you have the ln of b on the denominator as well.
And is that the formula you want to remember?
Yeah. So this is for the natural log, but this is the formula that we're looking at here for any logarithm. Notice the natural log fits in here, right? So really, it looks like we've got 3 different derivative rules. One for the natural log, or 4. One for the natural log, one for e, one for b to the x, and one for logarithm base b. But really, there's just those 2. You've got the derivative of b to the x and the derivative of the log base b of x. The natural log falls into this derivative here, and e to the x falls into the derivative of b to the x. So let's just look at that. Does this derivative f prime of x over f of x times ln b, does that actually hold when we're talking about y equals to the natural log of x? Well, think about the natural log as the log base e of x. And so the derivative formula says we take 1 over the argument, 1 over x, times the natural log of the base, times the derivative of x. So is that the same as for the derivative of the natural log? So it's all of this times this. Yeah, because what's ln of e is 1, derivative of x is 1. So this is 1 over x times 1 times 1, which is 1 over x. So although it seems like we have 4 different derivative rules, really it's just those 2. So do y'all have any questions on any of that? Let's see some examples then. Let's find the derivative of y equals to the log base 2 of 3x. So our derivative formula says that to take the derivative of the log base 2, 3x, it's 1 over the argument times the natural log of the base, which was 2, the base of the logarithm. So 1 over argument times natural log of the base times the derivative of the argument. So we have 1 over 3x ln 2 times 3, and we can divide the 3's out. You have 1 over x ln 2 as the derivative. Is there another way to approach this? can remember the formula for the log base 2, or log base b. But equivalently, we could write this as 2 to the y equals to 3x. So roll the log, convert it to an exponential. So that's an algebraically valid thing to do. Can we take the derivative of this? Can we take the derivative of 2 to the y equals 3 to the x, or 3x? Yeah, that's just another implicit differentiation problem. That's 2 to the y, ln 2 times y prime equals the derivative of 3x, which is 3. Solve for y prime. We have y prime equals to 3 over 2 to the y, ln 2. Oops. Okay. Why doesn't that derivative look like our derivative up here where it was 1 over x ln of 2? Yeah, because of the 2y. We're saying y prime in terms of y. We never want to write that out. What's 2 to the y?
3x.
Yeah. Two to the y power is 3x. So then we can cancel out those 3's, and we have 1 over x ln 2. Hopefully that's not confusing. I'm not trying to confuse anyone. There's just multiple ways to do these things. Once you have derivative techniques and remembering properties from algebra and pre-calc. Is there another way to look at that problem? Y equals the log base 2 of 3x. Oops. If I have the logarithm of a product, how can I write the logarithm of a product? All right, maybe I should review properties of exponents, or properties of logarithms. They're utilized a lot here. So can I write the logarithm of a product as the sum of the logarithms? So that's another way to look at this problem. The log base 2 of 3x is the log base 2 of 3 plus the log base 2 of x. And then I can take the derivative of the sum of two functions of x. So y prime equals, what's the derivative of the log base 2 of 3 with respect to x? It's a constant, yeah. Log base 2 of 3 is just some number. 2 to what power equals 3 is what that number is. So the derivative of this is 0. What's the derivative of the log base 2 of x? The log base b of x. Derivative of this is 1 over the argument times the natural log of its base. So again, we see the derivative is 1 over x ln of 2. So all three ways to look at that end up with the same derivative.
Can we use any of these ways?
Yeah.
Or are you going to like specify in the test like to use a certain way?
No, they're all equivalent. So the only calculus part is in taking the derivative. how we rewrite logarithms according to the properties. That's just I mean, you could consider that a simplification step, but it doesn't matter.
Should I never like use this specific method?
No, because they're all like, you know, either we can say, well, I'm just dealing with the log of this thing. Here's the formula to take its derivative, or here I'm just rewriting it, implicit differentiation. Here I'm splitting it up in terms of properties of logarithms. But at some point, you've got to know the derivative. So the only one that was slightly different was this one here, because notice when we wrote it as 2 to the y equals 3x, we didn't have to utilize any logarithm derivatives here, right? This is all just the derivative of exponential. And then that's just a result. Any logarithm can be written as an exponential. That's just the way it goes. So if y is the log base b of x, equivalently we can always say b to the y equals x. So either you can choose to deal with the derivatives of the logarithms by remembering the formula, or you can choose to deal with the derivative of logarithms by writing it out as an exponential form and then taking the derivative implicitly. So yeah, we can look at those. Any questions on any of this? If something there doesn't make sense, then just remember the formula. You can't go wrong just remembering the formula. What about the log base 8 of x squared?
Is it 2 over x ln b?
Yep. Or we can take the derivative of this thing as it appears to us. So I can say, well, the derivative of my logarithm, base 8, is 1 over the argument times the natural log of the base times the derivative of the argument. So I've got my 2x here. This is 2x divided by x squared over ln of 8. One of those x's on top goes away. All right, let me write this. So there's the inner function derivative over the function ln of the base. Or, since y is the log base 8 of x squared, we can rewrite that before we take the derivative. We can call that 2 log base 8 of x. And so y prime is that constant 2 times the derivative of just the log base 8 of x. So it's 1 over the argument times the natural log of the base. So that's 2 over x ln 8 as well. Any questions? Well, so another type of function that shows up in 3.9 and elsewhere. So let's ask the question, how do we take the derivative of y equals to x to the power of x? In general, the question would be, how do we take the derivative of y equals to some function of x to another function of x power? One solution to take the derivative of something like that, just first please note that that's not a power function because it's not x raised to a number, nor is it exponential because it's not a number just raised to the x power. It's a variable raised to a variable, so it's not an exponential or a power function. Let's note that these are not exponential or power functions. It's kind of both and, right? It's both exponential and a power function, but also it's a little different than both. One way we already know, we've seen a property that allows us to take the derivative of something like this. So we just got to remember, if I have x to the x, how can I rewrite x to the x?
X log of x?
Close. It does involve the logs. So I can say, let's just stick with y equals x to the x, just to make it simple. Or simpler, I guess. So the inverse property of exponentials and logarithms, you can write x to the x is e to the power ln x to the x. Okay, which is e to the x times the natural log of x. So that's beneficial because I know that the derivative of e to any power is e to the power times the derivative of the power. So we do get into the derivatives of these types of functions in this section. Always remember we can take the derivative of those functions this way. So this property here is utilized a lot. So that's one way we can look at those. The other way is a different technique to find derivatives. So maybe we can pause on this right here and just mention the fact that we can take the derivative of those things if we rewrite them in this form. And then maybe we'll come back to this. But first, we're going to look at a process called logarithmic differentiation. So, maybe at this point you're thinking, well, why do we need another derivative technique? So why another derivative technique? Somebody's mad. Maybe they just got a calc class. Why another technique? So in order to answer that question, let's just motivate that with a specific function. So consider the function y equals to, let's do x cubed minus 2x squared plus 1 to the 5th power times the square root of 3x minus 1 all over x squared plus 8 to the 4th.
Did you mean to put a 1?
Yeah.
What?
There's just a plus sign inside there.
Oh.
It's all messed up.
So in order to take the derivative of that function, what do we need?
Chain rule.
Quotient rule, right? Then a
Chain.
chain rule and a product. So consider that function. In order to take the derivative, in order to find y prime, we need quotient rule, product rule, and a chain rule. So there's, nothing, I guess, inherently wrong with that, right? It's like in theory, you already know those rules, so why don't you just use those to take the derivative? It's tedious.
There's so many little mistakes you can make.
Yeah, there's so many mistakes you could make in taking that derivative. So to answer the question, why another technique? Logarithmic differentiation, I'll just abbreviate that. Logarithmic differentiation can simplify the derivative process. Especially for functions like this, but just know that this is a valid technique, no matter what kind of function we're looking at. And there are some nuances that we don't really get into, but for us, know that this is a valid technique. Simplify the derivative process of functions like the one above. So exactly how does that happen? How does introducing logarithms simplify the derivative process of a function like that? So here you definitely have to remember the properties of logarithms. So the properties of logarithms by those we had three properties of logarithms. One that dealt with products, one that dealt with quotients, and one that dealt with powers. So the properties of logarithms can turn quotients, products, and powers into differences, sums, and multiplication. That's respectively. Quotients turn into differences, products turns into sum, and powers turn into multiplication. So instead of dealing with a function that has products, quotients, and powers, if we introduce logarithms and use their properties, we can simplify it to a function that just involves sums, differences, and multiplication. Does that make sense? So that's why we would want to look at this technique, because it can greatly simplify those more involved operations, especially in the context of a derivative. Okay, let's just look at an example. We might come back to that one, but it's more involved. So let's just look at maybe a simpler example, just to kind of get a feel for this. Then we'll write the steps down or the process. So let's now consider let's do x plus 1 over x plus 2 squared. So that's not something that you've probably seen something very akin to that in 3.4's homework. So the idea is now I'm going to introduce the logarithms so I can make use of their properties. So the first thing I have to do is I have to take the log of both sides of my function. Right? Hopefully that makes sense. To use properties of logarithms, I've got to get a logarithm in there.
You said of both functions?
Of both, yeah, because we're doing that to the equation. Okay. Now, there's nothing we can do at this point with just the log of y. But we do on the right-hand side have the log of a quotient. So we take the log of both sides and now simplify with properties of logarithms. So I'm going to go over here. We have the ln of y equals to the right-hand side is the natural log of a quotient. So like can rewrite that as the natural log of the numerator minus the natural log of the denominator. So that's one property of logarithms. I don't have a property for the sum of things, so the ln of x plus 1 is going to have to stay as is. But what can I do to this last term here?
Move the 2 out front.
Move the 2 out front because I have the log of something that's raised to a power. So that power, the square, can come out front and multiply this. Okay. So at least the right-hand side, that looks like a bit simpler of a function to take the derivative of, now that we know how to take the derivative of the logarithm. The issue we've got to pay attention to, though, is this isn't the original function. This is the natural log of the original function. But I've got a simpler equation here relating back to my function. So at this point, now that I've simplified as far as I can with properties of logarithms, I'm going to take the derivative of both sides. So take the derivative of both sides. With respect to x, the left-hand side where we had the ln of the function, ln of y, that becomes now an implicit differentiation piece. So what's the derivative of the natural log of y?
1 over y.
1 over y times the derivative of the argument. Yeah, 1 over y times y prime. Or you write that as y prime over y. It doesn't really matter. Okay. Equals to, what's the derivative of the natural log of x plus 1? I can't really fit that all in there. So derivative of the natural logarithm of whatever, right? 1 over the argument times the derivative of the argument. The derivative of x plus 1 is?
1 over x plus 1?
Yeah, 1 over the argument. Now the derivative of the argument.
1.
1. So the derivative of ln of x plus 1 is just 1 over x plus 1. Then we have minus 2 times the derivative. What's the derivative of the natural log of x plus 2?
1.
1 over x plus 2.
1 over x plus 2 times the derivative of x plus 2. Let's write this multiply. A lot simpler, right? That's 1 over x plus 1, 2 over x plus 2. But we're after the derivative. So what do we need to do here? To solve for y prime, I need to
Multiply the other side by y.
multiply both sides by y. We'll have to pick back up here on Tuesday. But please look over the properties of logarithms if you're not familiar with them, because they're heavily utilized here.